Thanks a lot to the organizers for inviting me. I'm very excited to be here. So I'm going to be talking about some recent stuff that I've been up to regarding dark matter direct detection. Um, Fun stuff with a lot of excellent collaborators. So I mentioned them all here. Joe Bramante, Jason Kumar, and Maxime Pospelov are theorists that you might know of. Ben Broerman is a PICO graduate student at Queen's University. Raphael Lang is a xenon one-ton experimentalist faculty at Purdue. I'm also part of I'm an external member of the DEEP experiment. And this is the working group that is looking for some of the signatures that I'm going to be talking about to look for dark matter. Okay, so here's a little map of the talk going forward. So first, I'm going to try to convince you that there's still a lot of room to explore on just this parameter space of the WIMP nucleon cross-section versus the dark matter mass as far as direct detection goes, where by direct detection, I mean detecting ambient dark matter in the flesh in underground experiments. Okay, so there's many orders of magnitude left for us to search for. And we do this simply by going to the optically thick limit of the detector. That is, we go to cross-sections large enough that dark matter is expected to scatter multiple times in the detector and leave different kinds of signatures. Now, this involves, on the theoretical side, paradigms that we actually know and love, paradigms that are just one or two steps away from the WIMP paradigm that has been garnering a lot of attention in the last 2 decades. On the experimental side, this would involve search strategies that are simple extensions to WIMP searches. Okay, so both on the theoretical and experimental sides, there's a lot of motivation for why we need to be thinking about looking for to cover more space to look for dark matter on just this parameter space. And then we're going to see that in this optically thick regime, we could also enlist even larger detectors, namely liquid scintillator neutrino detectors, to look for dark matter for us. Okay, and then if there is time, which I doubt there will be, I might mention how these strategies would also help us pinpoint the velocity spectrum of dark matter by collecting a lot of events. Okay, so I'm sure this audience doesn't need any convincing that dark matter exists, which we know from various pieces of cosmological and astrophysical evidence. And the million-dollar question is, does dark matter have any interactions with us at all outside of gravity? And one of the best answers we have to that looks like this. This is the current status of dark matter direct detection after 1,000 kilogram years of exposure and having used elements as heavy as xenon and so on. This is on the space of the cross-section for dark matter encountering nucleons versus the dark matter mass. And interpreting plots like these with a broad brush, you would say that the Z mediation is dead, because we seem to have come to cross-sections that are at the level of 10 to the minus 47, 10 to the minus 46 centimeters squared, like 7 orders of magnitude lower than what you would expect for a pure electroweak WIMP. But maybe Higgs mediation is just around the corner, right? Now, if you stare at this plot for long enough, you start wondering, could you extend this plot arbitrarily to pretty high cross sections and to like infinitely large masses? Obviously, the answer is no, because nothing in physics is infinite, because there is some assumption that we are making here that is breaking down. So exactly what assumptions are we making here? What really are the constraints? What really are the boundaries of this plot? Well, here is the current status of all the terrestrial experiments that have been looking for dark matter scattering. Okay, and as you could see, this is bounded on all 4 directions in the space for 4 different physics reasons. For instance, if you're looking at very low cross sections, then obviously dark matter is so ghostly that it doesn't interact with your detector too much, and you need to keep making your detector bigger and bigger and wait longer and longer, as Xenon 110 has been doing. And that sets the boundary here. If you're looking at much lower masses, sorry, if you're looking at low masses, especially masses much lower than the target nuclear masses, then dark matter is too powerless, doesn't have enough kinetic energy to trigger the detector above energy thresholds, and that sets your limitation in this direction. Up here, at very high cross sections, now dark matter might scatter with the overburden, that is the shielding of the detector or the Earth's crust or the atmosphere, so much that it might get slowed down on the way to the detector, and that way doesn't trigger your detector anymore. And to overcome that, you try to put your experiment on the surface of the Earth, or you try to send rockets, balloons, and satellites, such as seen in these bombs. Now, if dark matter is too heavy, then since we only know the mass density of dark matter, the number density falls inversely proportional to the mass, so that beyond a certain mass, dark matter is so rare out in the halo that throughout the runtime of your experiment, not even a single particle might have passed through your detector, leave alone scatter. So that sets the bound on this direction. And as you could see, the last time an underground experiment set the bound on the high mass frontier was DAMA, which was way back in 1999, just as they were getting into the modulation business. And given the exposure that they had, they were able to set a bound at a 10 power 16 GeV. Okay. So now, as a theorist, you would, or as a dark matter enthusiast, you would naturally ask, what if dark matter is hiding here? Are our experiments today capable of looking for dark matter at this high mass frontier? Can you push this high mass frontier? Right? So that idea has a lot of theoretical appeal, because we know that super heavy stable states do appear ubiquitously in theories of grand unification of forces. And there's also a lot of ways to make such super heavy dark matter in the early universe. There's already a lot of mechanisms, very attractive mechanisms put out in the market. To quote a few, there's Hawking radiation that you could get from primordial black holes. You could make them gravitationally at the final stages of inflation, which is the Wimps-Zilla idea. You could have preheating, which is parametric resonance that gives rise to a rapid decay of the inflaton that gives you a large abundance of stable particles. Or as Eric Kuflick and his collaborator had shown recently, you could even make these dark matter particles thermally in the early universe at these very high masses. And moreover, recently there's been this wave in the literature proposing models for these super heavy, strongly interacting and stable particles. So again, to quote a few, you have this electroweak symmetric monopoles or electroweak symmetric solitons in electroweak symmetric balls. You have charged primordial black holes, you have dark matter nuggets, blobs, or QCD charged composites, QCD charged fundamental particles making up dark matter composites, dark baryons, dark skyrmions, and so on. So why do we have this sudden wave again on the theoretical end? Well, that's because in large part, now experimental progress has attained a point where we can finally start thinking about detecting these kinds of particles. Okay, so this is largely a story of experimental progress. Now, getting back to DAMA, good. So there is a lot of theoretical motivation. Then can we now go ahead and search for this? So getting back to DAMA, the reason they were able to set a bound at 10 power 16 GeV was that they used a 10 centimeter times 10 centimeter crystal and waited for a year. That gives you an exposure that corresponds to this mass. However, today we deploy much larger detectors, right? Meter scale detectors such as liquid xenon time projection chambers like xenon 1 ton lux and panda X that are 100 centimeter in linear dimension. The largest dark matter detector is the deep 3600 liquid argon based detector at Snow Lab that has a diameter of 130 centimeters. There's also bubble chambers like Pico 40L that has a linear dimension of 50 centimeters and so on. And their runtimes do range in the order of years. So have these detectors already secretly set limits on the high mass frontier without us knowing it? Well, not so fast, because to set limits here, there is yet another effect of dark matter direct detection that we need to take into account. And that is the multiplicity of scatters in your detector. Recall that the number of scatters that you get in your detector per transit is given by the cross-section times the number density of the target material times the linear dimension of the detector. So given that in the cross-section versus mass space, there's always for a cross-section for a given detector above which you expect dark matter to scatter multiple times through in its transit. Whereas the WIMP searches look for cross-sections below that line, looking for a single scatter as it passes, as it goes through transit, if that scatter happens at all, right? So these are very different beasts for an experimentalist. Most often, the multiple scatter signatures are actually thrown away before the data analysis is done, because it's just a lot of energy deposit, right? So Goodman and Witten, when they proposed dark matter direct detection in 1985, they had already identified this effect, and they urged looking for this kind of signature for strongly interacting particles, and they gave you some details about how to look for them in sodium iodide crystals. And there's a classic line in that paper where they say a large range of masses for strongly interacting dark matter particles is probably already ruled out by the simple observation that sodium iodide does not glow in the dark, which comes from a lot of energy deposition. Now, when Dama in 1999 set their bound, they actually looked for this multi-scatter signature. Okay, by having two sodium iodide crystals a few centimeters apart and looking for coincident recoils. However, ever since then, this kind of multi-scatter signature has not been sought anymore, even though any experiment that looks for it, as you could see from this cartoon, just like that would be able to double the reach in the cross-section versus mass space in the log-log space. And that's simply because in the last 2 decades, we have been quite biased by the WIMP prior. Yeah, and that's exactly why all the underground experiments have been looking for only the single scatter WIMP signature. Now, having said that, how would multi-scatter signatures look like in current detectors? Let me begin with a simple illustration with the search that I'm involved in at the DEEP collaboration. So I'm not at liberty to go into details, but let me simply state that this could be done with a simple waveform analysis. Okay, so you basically look for several peaks in your energy waveform as the dark matter transits through the detector. And you use some clever cuts and variables, look for non-trivial trends, and you set some limits. And if this was done, if you do a back of the envelope calculation using just DEEP's dimensions and wait times and so on, what you find is that by virtue of being the largest dark matter detector, given a 1-year exposure, DEEP should be able to set a limit at just about the Planck mass, just about 10 to the power 19 GeV. Okay, and given the density of liquid argon and the size of the detector, the cross sections that DEEP should be able to probe should exceed 10 power minus 30 centimeters squared, and this is the per nucleon cross section. How about at other detectors? Well, at xenon time projection chambers such as Lux, Panda X, and Xenon 110, instead of a WIM signature that involves a combination of an S1, S2 peak, that is electroluminescence and photoscintillation peak, you would expect maybe a train of scintillation pulses and electroluminescence pulses, or maybe some merged pulses, depending on exactly what the multiplicity is. Similarly, at bubble chambers, instead of your stereo cameras looking for one single bubble, you're not looking for a track of bubbles. Okay, limited only by the limitation of your stereo camera or acoustic devices. And one cute thing about these searches is that the background, there's almost nothing that could actually mimic the signature of multiscattering dark matter, because you need something that's moving slow enough at 10 power minus 3 times the speed of light and depositing energy at every point that it scatters against. So you could think of, for instance, some daughter neutrons coming from radiogenic daughter neutrons of surrounding material or coincident electron recoils, but the count rates for these are essentially zero. And I'm happy to report that at both Xenon 110 and Pico, searches are ongoing for these kinds of signatures. Okay, so to transition to the next part of my talk, we now know that dark matter direct detection experiments are capable of looking for the signature and are already doing it. But we do have much larger detectors sitting around in our planet, namely neutrino detectors. Could these join the hunt for dark matter? Now, a few experimentalists, including Raphael Lang, have already set already set limits on the scattering versus mass plane using a neutrino detector, namely the germanium-based Majorana demonstrator, looking for this kind of a track signature with multiple hits. Okay, and here in this red region is their constraint. So given the exposure of the detector and given the energy thresholds and so on, and overburden considerations, they were able to already constrain dark matter masses of up to 10 power 15 GeV in this range of cross sections between roughly 10 power minus 28 and 10 power minus 25 centimeters squared. Now, this is a space that's been already covered by DAMA. Nevertheless, this is great demonstration that you could repurpose non-dark matter detectors to look for dark matter direct detection. Okay, now what my collaborators and I realized is that among all the neutrino technologies, liquid scintillator neutrino detectors are extremely suitable for doing dark matter direct detection this way. Because first of all, these liquid scintillator detectors such as Borexino and the future and the imminently operational Snow Plus and the future Juno would be at least 100 times greater in surface area than the largest dark matter detectors. That means just like that, you get 100 times greater mass sensitivity, right? Because the flux is proportional to the mass sensitivity. And that size could be inferred from these two pictures. This is Xenon 110 on the left, Borexino on the right. Both are in the Gran Sasso mine, and we've shown physicists for scale. Now, as for the cross-section sensitivity, all you need to do is to satisfy a selection trigger, which is the number of photoelectrons that you could detect within a given search window. So the higher the cross-section, the more the multiplicity of dark matter in the detector, the more the energy it deposits. So you just need to find where the cross-section is, where you could collect enough photons to satisfy the trigger. Now, if this search were done, and I have spoken to some Snow Plus experimentalists who have shown interest in this. So when the detector becomes operational, they have said that they could allocate some runtime for this. But if this were done, then just like that, with just 3 hours of running, just because Snow Plus is such a big detector, they would already be setting the world leading limits on dark matter masses. Okay, and go past DAMA. And if they were to run the experiment for just 10 days, that would already set a limit greater than a 1-year exposure of xenon 1 ton, and that would already get you close to the Planck mass. If they were to do this for a year, then they would much exceed the Planck mass, and so on. Now, how does the signal look like at SNO+? Recall that given the speed of dark matter and given the extent of liquid scintillator detectors, the dark matter takes about 10 microseconds to transit the detector. That's the length of the search window that you need to use for this. The signature would be nothing but a continuous deposition of photoelectrons over this transit time. Okay. And yet another thing that could help us is that since we are dealing with super heavy dark matter, to be clear of Darma's bound, and since the target is mostly carbon, dark matter is now coming in with so much kinetic energy that it's going to take a super collinear path as it goes through the detector. That is, you could calculate the angular deviation that comes out to 10 power minus 16 for typical dark matter parameters that we're looking for. And this collinearity could be exploited with the excellent timing information of like a nanosecond timing that these experiments have, which could be used for vertex reconstruction. Now, here's how signals would look at, say, Borexino in 10 microsecond windows. If I were to take dark matter with a per nucleon cross section of 10 power minus 28 centimeters squared for spin independent scattering, then typically for over a 10 microsecond window, I would expect photoelectron collection to look something like this. Okay, something like around 50 hits in the window. Whereas the main background, which comes from dark counts, which is misleadingly named, basically thermal fluctuations in in the PMTs. The main backgrounds would look like this, much less noisier than the signal at 10 power minus 28 centimeters squared. And only 1 in 100 search windows would have the main irreducible background of carbon-14 decays, which would look like this. Now, given these typical windows, given the the look elsewhere effect or the trials factor, only once in 10 years would you expect to see a window that is as noisy as the dark matter signal window from either dark counts or from carbon-14. Okay, so this is what I mean by an almost background-free search. So turning all this into sensitivities on the cross-section versus mass plane, here's what SNO+ would give us if they were to do this experiment. With the 10-year exposure, SNO+ should be able to go to masses all the way up to 10 power 21 GeV. Given the existing software trigger that Borexino has, if SNO+ were to implement that, they should be able to cover cross sections about 10 power minus 26 centimeters squared. Whereas if you were to actually put the look elsewhere effect into account and write a more sophisticated trigger, then you should be able to cover cross sections about 10 power minus 28 centimeters squared. For reference, I'm also showing bounds that have already been set via other probes. So the gray region here comes from looking for dark matter tracks from ancient mica dug up from deep under the earth. Over here is a bound from the Skylab experiment, looking for dark matter tracks in plastic etch detectors. Up here is looking for molecular gas clouds in the center of the Milky Way heated up by dark matter scattering. Okay, so there's still a lot of parameter space that could still be probed with SNO+ and xenon 1 for that matter. So I'm running out of time, so I won't transition into the next part of the talk, which is how to reconstruct velocity vectors. But the basic idea is that given such good timing information, you could reconstruct the velocity vector of every event And statistics is not a problem, because there's still a lot of room to play with. You could get up to 10 power 5 events. That means you could now use these velocity vectors to assemble distributions of the speed and angle of dark matter particles coming in. And that should help us do statistical analysis and get halo properties such as the dispersion speed, escape speed, and any anisotropies in the galactic frame and so on. So let me get to the conclusions of my talk. So the takeaways are that thanks to this amazing progress in experimental underground particle detection technology, meter scale dark matter experiments, as well as large scale liquid scintillator neutrino experiments should be able to probe dark matter up to the Planck scale or even beyond. And these involve a lot of well-motivated models on the market, such as composites and heavy baryons and nuggets and blobs and black holes, monopoles, solitons, and so on. And this cannot happen automatically. We need to do a dedicated search for multiscatter or track signatures. I'll leave it there. Thanks a lot. Happy to take questions.
Okay, yes, thanks a lot. So yeah, we have some minutes for questions.
I have one question.
Yes.
So in page maybe 28, where you had now the sensitivity.
Yes.
No, this one. Yes. So what happens now below cross sections of 10 to minus 28 or 29 now, which is the QCD cross section?
So okay, let me show with this plot. So below that cross section, at least for the SNO plus detector, you don't have enough hits to collect enough photoelectrons within a 10 microsecond window. So you don't have sensitivity at SNO plus. But you do have sensitivity at the dark matter detectors, which are capable of detecting much softer recoils. So at xenon 110, for instance, any cross-section about 10 power minus 33 centimeters squared, you could catch. A deep, any cross-section about 10 to the minus 30 centimeters squared, you could catch.
Okay, thank you.
Yeah, sorry. Maybe I misunderstood the question. You were asking about 10 power minus 24, maybe?
No. I was asking this. No, perfect. Okay, I understand.
Okay. Okay, great.
I have a question. Perhaps
yes,
I misunderstood something. How can you? So why you don't have the bound from an alpha particle or a neutron which is passing through the detector?
Just because
why you don't have this kind of background? Sorry, you said that it's zero background, but so how can you distinguish an heavy particle with respect to an alpha particle or a neutron which have the same cross section?
Right. So for alpha particles, the energy that you deposit is so huge that could be scrubbed out, and also it won't leave a track. It's going to be one giant energy deposition at one site.
Why this kind of particle do not leave all this energy? So you have the same cross section.
Yeah. But then there is no particular source of alpha particles that are just transiting, right? The thing that you might want to actually think, the thing that is closest to the dark matter particles is the neutron.
Yes,
that also has the
neutron.
same cross section.
Yeah, sure.
But the total flux of neutrons from the construction site or whatever is so small over the exposure time of the detector that it doesn't actually contribute to the background. That's the point. Also, the neutrons would be traveling close to the speed of light, whereas dark matter is traveling so slow that you could use timing information to tell this from the neutrons.
So you're basically telling me that the background of neutron, non-relativistic neutron, is so slow.
Yes.
That so it's not a problem.
No. I'm saying that so the neutron would be relativistically fast. As for the electron, the So for the electron recoils could already be distinguished from nuclear recoils at these experiments, at dark matter experiments.
Yes, I
The
know.
thing that might mimic the multi-scatter search is a coincident electron recoil. If you have two electrons going off at the same time. Now, the rate for that is also very small over the exposure of the detector.
Okay.
Okay. There's also a question by Roberto Franceschini in the chat. I don't know, Roberto, can you say it, or otherwise?
It's a bit noisy here. I hope it's not disturbing.
No, it's
yeah,
fine.
I just wanted to know, since you put vertical lines on the heavy side, what's the lowest mass that you can probe? So what is the vertical line on the left side of the plot? All plots start at 10 to 16 as far as I could see.
Yes.
So there must be a minimum mass that this strategy needs to
Right. The minimum mass is around 1 to 10 GeV, because that is the mass that you need, that much mass to start recoiling carbon atoms and shake them to produce photoelectrons. We didn't show them here simply because all that space has been already taken up, has already been ruled out by dark matter direct detection experiments, especially the DAMA experiment, which has done a multi-scatter search.
You're saying it becomes essentially a standard search, or it's another type of search, but it's just covering space that is being already excluded. I don't know if
it's not a so at these high cross sections, it's still not a standard search, but it's already been excluded by DAMA.
Okay, thank you.
Yep.
Okay, any other questions?
I have another question, just a curiosity. How
Yes.
this cross-section scale with the atomic number of the detector? You write spin independent, so A square, but so
Yes.
strong interaction.
Yes, so that's a slightly tricky thing.
Is pi r square, right? Is the geometrical
over
cross-section.
here we have assumed an A squared scaling. We have assumed that there is coherent scattering and there's A square scaling.
Is pi r square this cross-section? Is the geometrical cross-section?
So it's not geometrical cross-section, but you could also draw. So here we are assuming that it is that perturbative unitarity still holds, and that you have a nuclear coherence, and so there's an A square going on. But you could also draw a similar plot with just geometrical cross-sections with pi r squared as well. We haven't done it, but yeah, we could do it.
Okay.
Thank you.
The target is the carbon, sorry.
Yes, target is carbon here. Yes.